Hello everyone. For our project, Connor and I will be presenting to you finite element analysis of a jackstand. Car maintenance and repair is an inevitable process for every car owner. Enthusiasts, mechanics, and DIYers alike all rely on jackstands to support the weight of the vehicle while they are working underneath. The life of the user is dependent on the jackstand's ability to support the weight of the vehicle. Therefore, it is critical to understand the behavior of the jackstand while loaded in operation. SOLIDWORKS is an excellent software for complex geometry creation. SOLIDWORKS was used for part and assembly modeling in this project. Ansys engineering simulation software provides a high level of functionality for finite element analysis. Ansys Workbench and Ansys Mechanical were used for static structural finite element analysis of the jackstand. The geometry was created by using SOLIDWORKS and physically measuring a Harbor Freight brand aluminum jackstand. Each of the three main components, the jackstand frame, the ratchet bar, and the adjustment arm, were modeled separately. Simplifications were made to the adjustment arm geometry due to the fact that it was pinned inside the jackstand, making it difficult to access for measurement. An adjustment height for analysis was selected, and then the parts were configured to a SOLIDWORKS assembly, where contact between the faces of the components were defined. Since the jackstand measured was Harbor Freight's aluminum variant, the model was analyzed as aluminum alloy. Typical aluminum alloy has a Young's modulus of 71 gigapascals and a Poisson's ratio of 0.33. Fixed supports were defined on the bottom face of each of the four corners of the jackstand frame. Under real-world use, the jackstand can be loaded in a variety of ways. This is dependent on the shape of the jacking platform on the vehicle as well as the user. Multiple different loading techniques were examined, and a negligible difference was found. For simplicity, the loading of the top four flat faces will be used as pictured. Since the jackstand is rated for a 3-ton or 29,420 Newton force, this is the magnitude at which it was primarily tested. Since the typical car weighs only between 3,000 to 4,000 pounds, and a single jackstand will never be used to support the entire weight, the probability of overloading is highly unlikely under normal use. It is known that most small fillets do not affect displacement calculations. However, including these fillets on the geometry can significantly increase the complexity and necessary element density of the mesh. Our model was analyzed with a high attention to detail with fillets, then it was processed with most fillets removed. By using square edges, we were able to achieve a 59% reduction in necessary mesh elements while achieving extremely similar deformation results. The von Mises stress of these two mesh models were also analyzed, providing nearly identical results. The model with reduced filleting will be used for the analysis in this project. A mesh convergence study was performed with 4 different sizes of mesh by plotting von Mises stress. A coarse mesh, fine mesh, and very fine mesh were created by a variety of mesh element size definitions to the default mesh created by Ansys. 3,369 elements were used for the coarse mesh, 7,491 for the default mesh, 9,561 for the fine mesh, and 30,042 for the very fine mesh. As you can see on screen, the default mesh uses mesh elements of varying sizes dependent on the complexity of the geometry area. The 3 mesh types added for analysis use constant mesh element sizes throughout. This makes an imperfect comparison, but still provides a very useful reference point. Ultimately, it was decided to continue analysis with the default mesh as it seems to be the most appropriate optimization of mesh elements. Due to the complex nature of our geometry, TET elements were the type of elements used in our mesh.
Due to the complex nature of this geometry and important safety concerns of the product's application, The best way to validate the FEA results would be to do real-world testing. Some general hand calculations could be applied to give a ballpark idea if the model is accurate. Ultimately, the product should be manufactured and tested thoroughly in a variety of real-world conditions before it is tasked with the protection of human life. As you can see in the photo, one way of testing a jackstand would be testing how much force can be applied with a hydraulic press before the jackstand deforms or yields. The maximum deflection found in our model with a 29,420 Newton force is 0.443 millimeters. As you can see on the plot, this maximum was located at the top left region of the jackstand assembly. The average deflection throughout is 0.179 millimeters. A constant deformation scale of 64 was used throughout our results. A maximum von Mises stress of 156.63 megapascals was found in our model. You can see that there are high concentrations of stress distributed around the vertex of the cutout notches. This is what caused the head of the jackstand to bend towards the left. The average von Mises stress found throughout the model is 25.82 megapascals. Finding a perfect way to accomplish the mesh convergence study was not easy in Ansys. The program uses an algorithm in which it selectively defines mesh element sizes based on the part of the geometry. Since the only way we found to resize the mesh was defining element sizes as a constant throughout, we were unable to replicate the default mesh using varying element densities. A suggestion for improvement would be to render a more accurate geometry for the internal portion of the adjustment arm. It was inaccessible without damaging the shear pin in the jackstand, which would render it useless without repair. Our results show that the jackstand would have to be significantly overloaded before it presents any safety risk. This is under the assumption that the jackstand is being used with a basic level of common sense. Further analysis could be performed to determine how the jackstand behaves under improper loading, or how it would be affected if it was shock loaded by a car being dropped on it. Ultimately, it appears that a large factor of safety was kept in mind while the manufacturer selected the 3-ton rating.